So let's keep doing more derivatives in here. And this fourth example, it's asking us to differentiate sine up to x, sine squared x, and sine of x squared. Notice they look somehow similar, but notice the subtle differences that we have in here. So my advice, first of all, how about, look, I'm going to write or rewrite the function sine 2x, specifically the second term, sine x quantity squared. And well, this last term is going to be the same, sine x quantity squared. So and the reason why, let me discuss something pretty interesting here. So number one, every time you have trigonometric functions, my advice, put parentheses around the expressions that you have for sine, cosine, etc. Because if you look at this, okay, if you have sine x quantity squared, this is very ambiguous. To me, if I look at this, I'm not sure whether this is sine of x squared or if this is sine squared, or rather sine x quantity squared. So without the parentheses, it's ambiguous. I don't know what it is. So that's why on the example I have the parentheses, the power here in the trigonometric function, and here we have the power only of the quantity inside of the parentheses. So just my advice in this case. All right, so let's take the derivative of this function. Well, let's start. So we're going to do a couple of chain rules. So number one, what's the derivative of sine? Cosine. So in this case it's going to be cosine of itself, 2x. Okay, so for this first function, we have the outermost layer, which is, or the outermost function, which is the sine. We differentiate the sine, which is cosine. Then we're going to differentiate the second function, which is the inner. What's the derivative of 2x in this case? 2. So multiply by 2, which is the derivative of the inner one. Alright, to differentiate sine x to the second power, notice, well, we have some quantity to a second power. So essentially we should differentiate something like x squared, whose derivative is 2 times quantity to the 2 minus 1, which is 1. And that quantity inside of the parentheses remains the same. So what we did first is to differentiate the outer function. So now let's differentiate the inner function. And the inner, what's the inner function in this case? For the second term. It's sine. What's the derivative of sine? Cosine. So we're multiplying by cosine. And plus, again, the derivative of sine, which is cosine of itself, x squared. But this time, times the derivative of the inner function, which is the derivative of x squared. What would be that derivative? 2x. We're done with the calculus here. Is there anything interesting to simplify? Not really, maybe other than just writing the coefficients in front. And that's plus 2 sine x cosine x plus 2x cosine x squared. Final answer. Alright. So again, whenever having powers in trigonometric function, it's important to rather be specific with the parentheses, because just sine or any trigonometric function of x to some power without proper parentheses, we're not going to know which one is which. So letter E. What do we have? We have a radical function with a trigonometric and polynomial, an essential polynomial. So that's, we cannot differentiate this function just the way it is with the radicals. Number one, we need to write this radical as a rational power, which is what I'm going to do here. So can you please silence those phones? That's tangent x plus 4x raised to the 1/2. Alright, So what do we have? We have a composition function composed of two functions. An outermost function, which is basically something to the 1/2, and an inner function, which is tangent x plus 4x. So let's take the derivative f prime. That's 1/2 tangent x plus 4x, and 1/2 minus 1 by the general power. In this case, I'm indicating that I'm showing the setup because, well, with integers it's just easy to subtract 1 to any integer. Maybe for these fractions it might not be that easy. And well, we're going to multiply by the derivative of the inside of the parentheses. What's the derivative of tangent? Secant squared. And what's the derivative of 4x? 4. We're essentially done with the calculus. Let's just simplify 1/2 minus 1. That's going to give us negative 1/2. So that's 1/2. Let me write this. Okay, this is negative 1/2. Well, let me write the whole thing. Tangent x plus 4x to the negative 1/2 times secant squared x plus 4. So let's write the negative exponent to the denominator with positive exponent. But do we agree that once we write this as positive, 1/2 power, isn't it the same as radical? So let's go ahead and do that. That's a 1/2. Actually, I'm going to write this as a, well, let me do 1 over 2 times tangent x plus 4x to the 1/2 times this factor secant squared x plus 4. So number 1, I'm going to multiply this across, have it in the numerator, secant squared x plus 4 over 2 square root of tangent x plus 4x. And that's our final answer. Most of the times the calculus part of the problem might be the shortest part of the problem. The remaining part of the problem is usually a little bit of algebra. Alright. Letter F. So for a letter F, I claim we should combine a couple of rules. Okay, so which rules should we use in this case? Which one? Product rule. What else besides product rule? The chain rule at the same time, right? So we're going to combine two rules. And again, let's go back and write that product rule for us because, well, even though we have done it a couple of times, well, we're barely learning this. So how about we write it? So the derivative of the product uv, that's u prime v plus v prime u. That is the derivative of the first factor times the second plus the derivative of the second factor times the first function. So, okay. So h prime of x, that will be the derivative of the first factor. What's the derivative of x squared? 2x times simply e to the sine x plus the derivative of the second factor. So what do we have in this case? That's where the chain rule will kick in here. So number 1, the derivative of the exponential is always itself e to the sine x. But in this case, because this is a composite function, we should differentiate whatever we have in the exponent. What's the derivative of the exponent in this case? Cosine. But the story doesn't end here because that's only the v prime. We still need to multiply by, which is our u, right? That is x squared. So let me label everything here so you can see how this makes sense. So that's u prime, that's our v, and that's v prime, this is our u, all right? And I don't think there's anything else to do. Maybe factor out an x. Don't need to really factor out an x because that doesn't simplify much. So what I would do only is to have this x squared multiplying with in front of the exponential. This would be 2x e to the sine plus x squared cosine, I'm doing the exponential, so that's the furthest we can go. That's fine, that's an acceptable answer. And again, what did we do here? We combined the product rule with the chain rule at the same time. So this is what we're going to be doing as we move on, combining more rules. It's going to be the same case for letter G, because we have a couple of composite functions, you know, something raised to a power times something raised to another power. And at the same time, well, we have we have a product of two functions, so we're going to use the product once again. All right. So let's find the derivative of this product. I'm going to change the notation this time to dy dx. And well, let's find the derivative of this factor, of the first factor. So what would be the derivative of 2x plus 1 to the 5th power? So this would be the 5 goes in the front, 5 minus 1 is 4, the inside remains the same, 2x plus 1, but in this case by the chain rule we're not done, because we still need to multiply by the derivative of what we have inside of the parentheses. What's the derivative of that? 2. Okay, multiply by 2. But that's only the u prime part of the product rule. We need to multiply by v, x cubed minus x plus 1 to the 4th power, plus, let's do the second part of the product rule. In this case, we're going to do another chain rule, which in this case, that's something to the 4th, that's a 4 times the something to the 4 minus 1, which is 3, subtract 1 to the exponent, keep the inside the same, but multiply by the derivative of the inside. And what's the derivative of the inside? 3x squared minus 1? But that's only the v prime. We still need to multiply by u, which in this case is 2x plus 1 to the 5th. And again, let me label it so you can see the product rule in action again. So this is u prime v plus v prime u. Are you guys following me here? Is everything making sense? Okay, so how do we simplify this madness? Well, number one, I mean, if you want, but you don't want to foil this trinomial trick, you don't want to do that. Instead, we're going to factor the greatest common factor. So let's identify the different factors. I'm going to highlight with different colors so you can see the different ones. So number one, okay, let me use this yellow. So we have factors of 2x plus 1 and 2x plus 1, and we have common factors of x cubed minus x plus 1, x cubed minus x plus 1. So I'm going to factor out the lowest, so like GCF we factor out the lowest power of each. So in this case, let's factor the 2x plus 1. Okay, so between power 4 and power 5, we can factor out up to power 4. Do we agree? Because we can factor the 5 powers, because here we only have 4. So the maximum we can factor out is 4. Okay. So for x cubed minus x plus 1, we have it here to the 3rd power versus to the 4th power. So let's factor out the cube. Okay, I'm going to open brackets and write down whatever we were left with. So we were left with the product between 5 and 2, which is 10, and because we factored 3 powers of this, we're left with 1. plus 4. And in this case, well, we factor the 3 powers of this trinomial, so we don't need to write any powers of the trinomial, so that's fine. This 3x squared plus 1, I mean minus 1, wasn't factored out. And out of the 5 powers of 2x plus 1, we factor out 4. That's 2x plus 1. Simply one more power, and we can leave it like this. Yes?
The actual exam, are we allowed to put our, leave our final answer into
Like the first step, maybe at least reduce the 5 times 2. And over here, okay, there's nothing else. Maybe as far as that. Yeah, because over here, we would have to FOIL this and distribute the 10, combine a lot of like terms. Well, that's going to take us a whole lecture to do, right? And I really want to move on to other topics. The idea is that you see how we are combining different differentiation rules. In this case, we're combining a product rule with a couple of chain rules in this case, right? So that's the main point in here. The remaining, I mean, doing everything else, that's just algebra, you know. Well, you guys already did back in pre-calc or I don't know, algebra in high school, whatever, right? Well, so far we have worked with functions that contain like only 2 layers, you know, an outermost function and an innermost function. But of course, we can go really crazy about composition of functions. So we're going to take the derivative of this couple of functions. So how are we going to look at this function? Well, let's look at the different layers in this case. All right. Let me highlight using different colors. Okay, so we have the outermost function, the outermost layer, which is something, whatever something it is, to the 7th power. And then the next function in the layer, the next layer will be the tangent function. And then the next layer, it's the exponential. And then the inner layer would be the cosine. And finally, the innermost function is the x to the 5th power. So how are we going to differentiate this? Well, again, these nested dots are going to help us visualize what we're going to do. So let's differentiate the outermost function. So that's something to the 7. How do we differentiate something to the 7? Well, we're essentially differentiating x to the 7, and the derivative of x to the 7 is in it 7x to the 6 by the general power rule. So that's what we're going to do here. Y prime equals 7 times the madness we have in here to the 6th power. And that madness remains the same, tangent of e to the cosine of x to the 5th. Alright, so that we just differentiated the outermost layer. So let's look at the next layer. The following layer, or the following function, is the tangent. What's the derivative of tangent? Secant squared, alright, times secant squared of, well, the madness is getting smaller every time. Alright, so we're done with differentiating the secant. What's the next layer in this case? The e. Okay, so we differentiate the e. One more. What's the derivative of an exponential? Isn't it itself e to the cosine of x to the 5th? Alright, so what's the next layer? Cosine. What's the derivative of cosine? Oh, shoot. Negative sign. Alright, times negative sign of x to the 5th. And the last one, what's the derivative of times 5? Well, let me make some room over here. Five x to the 4. So we're done differentiated 1, 2, 3, 4, 5 layers. So we have a function composed by 5 functions, 5 layers. Would you see something like this on the exam? Maybe nothing too crazy, But I mean, the concept here is that you can see that all we do is just multiply by the derivative of the following layer and then the following layer. Ultimately, there's really nothing to simplify other than the 7 times 5. That's all we have to simplify over here. And well, I really don't want to write the whole thing. Well, I'm going to do it instead. 7 times 5, that's 35. I'm going to write this x to the 4th in the front. And then the rest is simply tangent of e to the cosine of 5, x to the 5th, to the 6th, secant squared e to the cosine x to the 5th times cosine of, that's e to the cosine x to the 5th. Actually, check this minus sign. Minus sine x to the 5th. That's the only thing we can do about simplifying this function. Alright? The reason I brought up a function this crazy is so we can see, how can we extend this chain rule, how it works. Question?
Where the subtraction sign goes?
It went to the front. Mm-hmm. Yeah. So again, there's not much to do. Let's look at this nested radical function. So we have how many layers? So an outermost radical, an inner, and then an innermost. So the best way to go about a function like this is to write all the radicals in terms of rational exponents. So that's x cubed plus root. Okay, that's something to the 1/2. The overall radical means to the 1/2. That's x squared plus x to the 1/2 and to the 1 to the 1/2. Alright? Oh, I forgot the other 1/2. So number 1, let's differentiate something to the 1/2. That is, the 1/2 goes in the front, and we will need to subtract 1 to this 1/2. So dy dx equals 1/2 quantity to the, what's 1/2 minus 1? Negative 1/2? Alright, sounds good. So this quantity with this same madness right here inside, x squared plus x to the 1/2 to the 1/2. Now, let's differentiate this whole thing in here. Let's do one at a time. So we need to differentiate this. What's the derivative of x cubed? 3x squared plus the derivative of this composition. We still need to differentiate more compositions. Well, on the one hand, this 1/2 jumps in the front, and x squared plus x to the 1/2, and that's to the negative 1/2. Alright? Now we need to keep differentiating this, and then the next thing to differentiate is this part right here. We don't be careful not to differentiate the whole thing, only the quantity inside of the parentheses. Well, in this case, that needs to be differentiated here. The derivative of x squared, 2x. The derivative of x to the 1/2, isn't it? 1/2 x to the negative 1/2. And we're done with all the different layers. Right? So that's essentially the chain rule. We are like connecting by means of a chain, if you will. So that's why we call it the chain rule. Alright, so let's go ahead and simplify this madness. I mean, there's nothing like to simplify other than just writing the negative exponents to positive exponents, and then those rational exponents to make them look back like radicals. Alright? So let's see. So that's going to be 1 over 2 times this whole quantity x squared plus x to the 1/2 when I'm going to go back to radical x, and this quantity to the 1/2 I'm going to write it back as a radical, and that's to the 1/2 in the first place, times, okay, this quantity to the negative 1/2 becomes a quantity to the 1/2, 3x squared plus 1/2 x to the x squared plus root of x to the negative 1/2, the whole thing to the 1/2, so 1 over that, alright, times 2x plus 1 over 2 root of x. And again, because there's really not much to do about simplifying this, especially because I'm going to get a complex fraction. This one I'm not going to leave it like this. At least this one I'm going to go back to write it as radical. Oops. That's 1 over that. Of course, I mean, I don't think you're going to get anything this complicated on a quiz or an exam. The reason I like doing this, so you can see again how the chain rule works with more composite functions. So once you get an understanding of these crazy looking functions, the ones that you see on the homework, trust me, they will look more friendly in comparison with this. And let's see, is there anything else? I think this is it for the chain rule. Questions before moving on to the next topic? Yes.
Why is the 1/2 included?
Which one?
On the left side.
This one?
Yeah.
Oh, that should be, thank you. That should be outside. Next. Okay, let's move on to the next topic, and the next topic is section 3.5, implicit differentiation and derivatives of inverse trigonometric functions. Well, all right, so what about implicit differentiation? So everything which will start with the question that can we find the slope of the tangent line at x equals to 3 for this circle? So that's 1, 2, 3, 4, 5. Well, the question is, well, at x equals to 3, we have an issue here. What do we have? The problem is that we have two possible answers at x equals to 3. So which one are we going to be looking for? Well, it will depend on the actual point, on the actual order pair for which we want to find that slope. All right, so let's see. In this case, notice this is an equation. This is not a function. In fact, all for the derivatives that we have been found in these few sections, for example, f of x equals x cubed plus 5, for example, g of x equals e to the negative x squared, for example. These are called explicit functions. And this is because we can express y as a function of x. We can solve for x, and we can solve for y explicitly. The problem with this equation right here, x squared plus y squared equals 25. So that's x squared, that's an x squared plus y squared equals 25. If we try to solve for y to define y as a function of x, we're gonna get the following. So y squared equals 25 minus x squared, and what happens? What do we do to get this y by itself? Square root, right? Square root of 25 minus x squared. Is this correct? I'm missing something here. What am I missing? Plus minus, right? So this is a problem here. We are obtaining essentially two functions. Negative root of 25 minus x squared and positive 25 root of 25 minus x squared. And in this case, the problem is we are not obtaining a single function. We cannot write this function as an explicit function of y. So in this case, we're going to call these functions implicit functions. And there's a process to get the derivative for an implicit function, because I mean, look at the picture. In order to find the derivative, the derivative gives us the slope of the function at the given point. And well, so in this case, if we look at this circle right here, there's some steepness at every single point. So we should be able to get the derivative. The question is, how do we do it?
Yeah, so there are two tangents and it's implicit. There's one tangent and explicit.
So in this case, we will be very specific at one of the points, because in this case, we can find the tangent at x equals to 3, number 1, for the point 3 comma 4, or I mean 3 comma, I think it's 3 comma 4, or 3 comma negative 4. All right, so we would be specified at one point. So let's see. How do we go about implicit differentiation? Well, number 1, let's keep doing more chain rule. It's important to get used to the notation that we're going to do to put together the chain rule along with this implicit differentiation. Well, so the derivative of f of x to the third power. So this is a composition function composed by the outermost function, or the outermost layer, something to the third power, and an innermost function which is just some f of x. This is not like the other examples that we got, like x squared plus 1. You know, we got something like this. This time it's just some function f of x. So to differentiate this function, this will be 3 times something to the second. The something remains the same, but what else do I need to do to complete the chain rule here? What was that?
Derivative of the inside.
And what's the derivative of the inside? What the derivative of f of x? Just f prime, right? That's it. All right, just f prime. All right, so we will need to have an understanding of what we did here in order to fully understand what we're going to do with implicit differentiation. All right, so let's do another derivative, another weird derivative, but in this case, notice we're going to have an equation. We're not going to be able to solve for f in this case. So what we're going to do in this case is differentiate both sides, and this is valid because recall, whenever we have an equation, whatever you do on one side of the equation has to be done on the other side of the equation. That is, add or subtract, multiply, divide, cube, take a square root, ln, exponentiate, you name it. So it should be true as well for the derivative. So we're going to differentiate with respect to x, the quantity x squared plus f of x squared equals the derivative with respect to x of 25. Okay, let's do the easiest side. What's the derivative of 25? 0. Good. Okay, let's differentiate x squared. What's the derivative of x squared? 2x. All right, what's the derivative of f of x to the second power? So first of all, 2 times f of x to the first power. And what else do we need to do to complete this chain rule? Times f prime of x. All right. Yes, I forgot the x. Thank you. So that's 0. All right. So our goal is to find an expression for f prime, because again, f prime is the derivative, and the derivative means slope, and we want to use this expression to find the slope, in this case of the circle that we had on the at the beginning in the example. So let's solve this equation for f prime of x. Alright, so I'm going to subtract 2x on both sides. That's going to give us negative 2x, and then I'm going to divide. So I did subtract negative 2x, and then I'm going to divide both sides by 2f of x. So this will be f prime of x equals, cancel the 2's, negative x over f of x. Are you guys following me here up to this point about what we're doing? Okay. Now the question is, what if... the question is already written. So the second part of the problem, what if we replace f of x with y? Because I mean, that's what we have been doing throughout all our lives, taking algebra, intermediate algebra, pre-calc, you name it. Y always represents the x or vice versa. So what I'm going to do, I'm going to represent this function or this result. Oh, actually this is prime, and this will become f prime of x equals to negative x over y. Alright, and that's our derivative of this implicit function. Now let's give a definition for this implicit differentiation. So that's the next topic over here. Alright, the method known as implicit differentiation, in this case, is going to permit us to find the derivative dy dx of y prime without solving the equation for x, like in the previous case, like at the beginning of the problem. So at the beginning of the problem, what did we do? We tried to solve the circular function. Well, actually it's not a function because fails the vertical line test, right? So it shouldn't be called a function. In this case, it's just a relation and described by the equation x squared plus y squared equals to 25. In this case, we failed to get y explicitly as a one single function of x. So that's why this is an example of an implicit function. So what we're going to do, what the method is to differentiate both sides of the equation, and whenever we differentiate something in terms of y, we do a mini chain rule and multiply by dy dx. So let's look at some of the examples. Okay, so find an equation of the tangent to the circle x squared plus y squared equals to 25 at the point 3, 4. And actually we already got the result for this derivative. Didn't we do it in the previous part? So let's just go ahead and use that result. So from before, y prime equals negative x over y. So we got the derivative from before. Now we need to find the equation of the tangent line. Now, to find an equation of a tangent line, there's two pieces of information. What are those two pieces of information? The slope and what else? And a point. We got a point, but we don't have the slope. However, we have an expression to compute the slope. So y prime evaluated at the point 3, 4, and in this case, negative x, which is 3 over 4. So that's equal to the value of the slope. So let's just use y minus y1 equals m times x minus x1. So y minus 4 equals negative 3/4 times x minus 3. And we can leave the equation like this, right? I mean, you can distribute the negative 3/4 and then add 4 to both sides, and that's going to give us the equation. So coming back to the initial picture, we're actually looking at this equation of the line. So let me use a different color. So that's y minus 4 equals, I'm not going to have enough space. y minus 4 equals to negative 3/4 x minus 3. So that's our equation here. So that's how we get the equation of a line of our relation that does not describe a function that in this case we cannot solve for y explicitly, so we have a new method question.
So whenever it's x squared plus y squared, do we need to always use y prime plus negative x by y?
Yes. So if we want negative x over y, so that's the one we use to get the slope. If they were asking us for this equation, we would have used this point instead. All right. So let's see what's next. The next example, another find the equation of the tangent line for this equation, and I mean check this out. Just try to solve for y over here. So I'm gonna move x cubed to the other side. That's y cubed equals 6xy minus x cubed, and then the one that contains the y, I'm gonna move it to the left hand side. So that's minus 6xy equals negative x cubed. So I'm gonna factor out the y, and that's gonna give us y squared minus 6x equals to x cubed. Do you see the problem here? In this case, we cannot express this equation as an explicit function of y. There is no way we can do it. For this reason, we will have to use implicit differentiation. However,